Hello everyone, welcome to another lecture of the subject control system. In previous lecture we discussed about obtaining transfer function of electrical systems with the help of impedance, and there we saw various voltage current relationship of individual element like capacitor, inductor and resistor. Then we went to the transfer function, and in transfer function we discussed about three forms. Actually we discussed about two forms in the previous video, but I said that there is actually three forms of transfer function. The third form, that is the time constant form, will be discussed in this video. So let me do a small recapitulation of the previous video, that any resistive element has impedance of R, any capacitive element have impedance of 1 by SC, and any inductive element have impedance of 1 by impedance ZL equals to SL. So this was obtained from the different individual voltage current relationship of the individual elements. Then we went to transfer function forms. There we denoted that transfer function can be written in this form, ns by ds, where ns can be written as an mth order polynomial, as you can remember, mth order polynomial, and ds can also be written as another polynomial of order n. When we represent any transfer function like this, that form is called actually polynomial form of transfer function. Then we discussed about pole and zero. So in pole and zero we denote transfer function as like this: s plus zi, s plus z1, s plus z2 up to s plus zm, then s plus p1 plus s plus p2 up to s plus pn. This was the transfer function. And the roots of the numerator polynomial, that means ns, is was called the zeros of the transfer function, because at these points z1, z2, zm, that is actually minus z1, minus z2, minus zm, the transfer function becomes 0 because the ns becomes 0, and at these points minus p1, minus p2, minus pn, the ds becomes 0 and the transfer function becomes infinity. So these points called as poles of the transfer function. So we discussed about pole and 0 with mathematical interpretation a bit advanced level, in a bit advanced level. Now I am going to discuss the time constant form. Time constant form of transfer function. What is time constant form? First let me discuss what is time constant. So for any system, any practical system, before reaching the output to a desired value or to a steady state value, the system takes some time to reach its output value, and that means to reach its desired value. That means, for example, consider a ceiling fan. You are turning on the switch. At the moment you are switching on the fan does not move at its highest speed, but it takes some time to reach its highest speed. So that time is a delay involved in the system, and while analysis of any kind of system, this delay must be taken care of. So we define a term as time constant to indicate this delay of any system. Okay, so there is some suitable mathematical equation, mathematical definition of time constant, but I will not go deep into time constant, definition of time constant in this chapter, but there is a chapter of time domain analysis. There I will discuss advanced level time constant concept. Okay. Now, what is time constant form? Actually, as we have seen earlier, that any transfer function can be represented in terms of poles and zeros. Okay, so poles and zeros are the key element to contribute to the time response of the system. Okay, so every poles and every system is contributing to the time constant of the system. So let me write down the pole zero form first. S plus z1 k into s plus z1, s plus z2 up to s plus zm by s plus p1, s plus p2, s plus pn. This was the general pole zero form of the transfer function. Now this z1, z2, zm, pn, p2, p1, each and every element contribute to the time constant of the system. So we can write, and the time constant is actually reciprocal of these elements. So if you can let us consider a single factor, let's say s plus p3. This is a single factor. Now if I take p3 as common, then it will be s by p3 plus 1. Now this 1 by p3 term, 1 by p3 term is called time constant due to this pole p3, that means time constant due to p3. So this can be written as p3 s tau p3 plus 1, where p3 is the pole and tau p3 is the time constant due to the pole p3. So I can write each and every term in this form, and taking common all the pole values and all the zero values and the k, we will combine it together and we will denote another constant, that is, let's say k tau. It is gain constant of time constant form. Okay. For generalized things, we used k as in pole zero form as a gain constant. Now we will denote another constant k tau, where all these common term will be combined there, and the transfer function will look like k tau t of s equals to k tau s tau z1 plus 1, s tau z2 plus 1, so on, s tau zm plus 1, s tau p1 plus 1, s tau p2 plus 1, and up to s tau pn plus 1. So this is the general form of pole zero representation of transfer function. This is the general form of time constant representation of the transfer function. Now this polynomial form of transfer function, this time constant form of transfer function, this pole zero form of transfer function, individual have some individual significance in analysis of control systems. That will be discussed in this context, where whenever needed and when the analysis portion will come. As of now, just remember that there are three different forms of transfer function. One is time constant form, another one is pole zero form, and another one is polynomial form. Okay, next, after discussing this third form of transfer function, I want to take some example circuits to show you how to solve questions. Okay, let's say I have a series RC circuit. Let's say this is the very basic example. Okay, let's say voltage across the capacitor is my output and this is the input voltage. Okay, so what will be the transfer function? V naught of S by Vi of S I need to calculate. So how will I do that? See, first we will convert this into Laplace domain. That means the individual element will be represented by its corresponding impedances. So R have impedance of R and C has impedance of 1 by SC. Okay, and VIT in Laplace domain will be converted to Vi of S and V naught T will be converted into V naught of S. So now using voltage division principle we can calculate Vi of S, V naught of S, that is 1 by SC by R plus 1 by SC. Let us simplify this one. 1 by SC, here it is SC, RSC plus 1, SC gets cancelled and it will become RCS plus 1. So this is the transfer function. Now let me do a little bit analysis of this transfer function. So the transfer function of this system is tau s RCS plus 1. So what is numerator ns of s? What is ns here? It's simply 1. What is the order of numerator? That means m. M is the highest power of s in that expression. So what is the highest power of s? It is s to the power 0, right? So m is 0. Now what is ds here? Ds is 1 plus RCS. Now what is n? The value of n is here 1 because s to the power 1 is the highest power of the s. 1 is the highest power of the s. So the order of the system, what is order of the system? Order of the system is either m or n, which one is greater, that is the order of the system. Maximum between m and n is called order of the system. Order of the system. So what is the order of the system? Order of the system is the highest power of s either in the numerator or in the denominator. Often you might have heard the sentence like that: order of the system is the highest power of s in the denominator. Why is it like that? Because whenever any practical any practical scenario is there, any practical system transfer function is there, it always seen that the value of m is lesser than value of n, or it is equal. Then that means m is lesser or equals to n. So when it is equal, so maximum of m and n, it both are same. That means order is equals to m or n, anything. When m is less than n, then maximum of m and n will be n here and the order will be n here. So look carefully, order is always coming as n, whatever be the situation, whether m is less than or equal. Okay, m greater than n is not possible. M greater than n is not possible, and it is not actually realizable system. Practically any system we are designing, we want to realize that system practically. So practically m greater than n is not realizable system. That's why it is not considered, and n is considered as order of the system the total system has order as n, because n is always greater or equal to. So the order of the denominator polynomial itself is the order of the system. So what is the order of the system? In this system the order is n, that means 1. This is the first point, this is the first observation from this circuit. Okay, now there is another observation. What is that observation? Let me write it here again. Transfer function Ts equals to 1 by RCS plus 1. Look, there is 1 0, actually there is no 0 at there is no 0 of the transfer function, and there is one pole of the transfer function. Obviously m is the number of zeros and n is the number of poles. So if a system has order 1, then it will be having only one pole of this form. Now if it is something like s plus 1 and in denominator RCS plus 1, then the order would be still m equals to n equals to 1, but there will be a 0, a pole. But in this system we have only one pole, and the pole is at, let equate it to 0, and s equals to 1 by RC minus 1 by RC. So I can write this system as, okay, this system this is a pole, so write me it as P. So I can, in this is a polynomial form, and I can write it as pole 0 form like this, S minus P. S equals to P, it is the pole, so S minus P is the factor. So what it will look like, S plus 1 by RC. So this transfer function can also be written as this, as obviously by some simple mathematical manipulation we can arrive to this equation. Okay. Now again, one more thing. I have done a bit mistake. Then there must be a k. This will no longer be 1, right? This will no longer be 1. The k value will be added, as in general form we use this term. So what will be the value of k? By manipulating this mathematical expression, we will arrive to this expression and we will see what is the value of k. We can easily see, and then we can again go to another form, that is 1 by s tau p plus 1. Again look at this term. This is in this form only. I have arrived to this transfer function earlier, 1 by RCS plus 1, and this is itself the time constant form. And what is the time constant? Tau p is equals to RC. I think you have heard the term time constant in network theory. There we used to say that in an RC circuit the time constant tau is equals to RC. Look at here, tau p is equals to RC. This is the time constant of the system. So by analyzing transfer function we can analyze this much of a system. We can analyze pretty much everything from a system. But one assumption must be there, that the capacitor initially doesn't have any charge. If it has some charge stored previously, then the analysis would be something else, and that is not that will not be covered in this portion, in this lecture. Okay, let me take another circuit. Now we have seen an RC circuit, now let us take an RL circuit. RL circuit. Okay, VIT is the input. Now one thing, capacitor actually stores charge. Okay, excuse me please. Capacitor actually stores charge in terms of voltage. So voltage across the capacitor is so much important for us to analyze an RC circuit or an RLC circuit or any circuit comprising of capacitor. The voltage across the capacitor is of so much importance. So we consider often for simple RC circuit or RLC circuit, we consider voltage across the capacitor as an output. Similarly, L stores magnetic energy in terms of current, and that current is of importance for us to analyze any circuit consisting inductive element. So here IT I will take as output. Okay, this is output. So what will be the transfer function here? The transfer function will be I naught of S by Vi of S. Let us obtain the transfer function. Let us obtain it. As it is a series RL circuit, obviously I naught T will flow through the whole circuit, and let us convert this to Laplace domain. R will be R, and L, as we have said earlier, that the corresponding impedance of L is SL. And it will become I naught of S, capital I naught of S, and because this representation is the Laplace domain representation, so all the time domain variable, all the time domain function will be converted into Laplace domain functions. Now by using simple Ohm's law, we can calculate what is I naught S. I naught S into Z equivalent is equals to Vi of S, isn't it? So what is I naught S by Vi of S? It is equals to 1 by Z equivalent. So what is Z equivalent? Z equivalent is, this is series combination of R and SL, so it is R and SL. Again, what is the transfer function? R plus SL. Now this is simple polynomial form. We can convert it into pole zero form like this. R is taken common here, so 1 plus, sorry, L is taken common here, so it will become S plus R by L. Yes, sir. Okay. Now the pole is at S equals to minus R by L, and in pole zero form I was giving you the constant K. Here the value of K, look, here the value of K is 1 by L itself, because this L can be in the numerator side like this. So here K value is 1 by L. As I am manipulating this equation from this equation, so I didn't consider K here, because the K will of the function of L, so there the value of L will be there. Okay. So what is the pole? The pole is at S equals to minus R by L. Again, one more thing, this is the transfer function we obtained. Now what is the time constant form? The time constant form is S tau plus 1, 1 by S tau plus 1. So that means R must be taken common, and it will look like 1 plus S L by R, isn't it? So again this R can be written here 1 by R, and it will be K tau, as I mentioned earlier that there will be one constant K tau, and K tau is, let me draw it here, that will be much more easy to visualize. k tau 1 plus is L by R. So what is the value of k tau? K tau is 1 by R here, this value. Now what you can see from this equation, the time constant of a series RL circuit is L by R. Compare this equation with this will be k tau. Compare this equation with this, tau is equals to L by R, isn't it? And again, like RC circuit, you might have been told that for series RL circuit the time constant of the circuit is L by R, and here it is L by R. I think the time is over, so let me close this lecture today. So let me give you a brief summary of what we have done today. Is we discussed the time constant form, and then from time constant form we know that for individual pole and zero they individually have some effect of the time constant of the overall system. Then we discussed about series RC circuit, and we arrived to the transfer function of the series RC circuit, and then from that transfer function we analyzed what will be the pole value, that means where the pole is located, and what is the time constant. Then we do similar thing for series RL circuit. Okay, so this much for today's lecture. See you in the next lecture. Thank you.